All right, so we're going to take a look at the next few sections. But first thing, we're going to roll back and we're going to cover a little bit of the basis for where the derivative of sine x came from. I know you had some Khan Academy assignments, so you're probably comfortable with the fact that the derivative of sine is cosine. But I want to give you some basis for that. So first thing to do that, we're going to have to establish two limits. One of which we're very comfortable with. This is the one that we used the squeeze theorem to prove earlier in the year, and that's the limit as x goes to 0 of sine x over x is 1. But then the second one is one that we did not actually spend any time with because we're going to learn another limit technique that's going to make these two limits really almost unnecessary later on in the year. It's called L'Hopital's rule, but we need to establish derivatives before we can do that. But this second limit can be shown through the conjugates method. So multiply by a cosine x plus 1, top and bottom, and then work your way through the limit, and you will get that that limit equals 0. All right, so we're going to lean on those two to help us with the proof for the derivative of sine x. So let me get a pen here real quick. And we're going to start off with the h approaches 0 definition. So we've got limit as h goes to 0 of sine x plus h minus sine x all over h. All right, so this is when our memories from past math classes should kind of start to spark a little bit, that there is something we can look up. It's not a fact that I'd consider like a memorized fact. To be honest, I look it up every time just to make sure I don't mix it up, because I know there's sines and cosines and either pluses or minuses, but if you're not using it every day, it's really easy to make a mistake. So sine x plus h gives us a sine x cosine h plus a cosine x sine h. All right, then we still have the minus sine x there in the top, and we have an h in the bottom. All right, so with one trig identity we get to here, and from this point what we're going to do is we're going to try and just rewrite this. So in class setting we'd go through a lot of like, what do you think we should do? And usually what people will get to is the one move they see as a possibility is to group and factor a sine x out. So we're going to go ahead and do that. We're going to move this first and last piece together. All right, so I've got sine x cosine h minus sine x, the first and last piece. Then I've got plus cosine x sine h. And that's all over h, but I'm going to make a choice here to split this so that we've got the first two terms over h and the second and the last term over h. Now, if you think about how we could rewrite this, we could really, push this back together. It already has a common denominator, and it would go right back to where we were. All right, now in the first chunk of this, I'm going to go ahead and I'm going to factor out that sine x. So I've got sine x times, and I'd be left with a cosine h minus 1 over h. And then in the second piece, I'm going to take the cosine x out front, and that leaves me with the sine h over h. Now, what we hopefully notice is that in here, we have the two structures that were up in those limits. So this first one, we know would go off to a 0. All right, this second one, we know would go off to a 1. So if I apply that limit, I would end up with sine x times 0 plus cosine x times 1. All right, which would result in cosine x. All right, and that would be our basis for the fact that f prime of x equals cosine x for f of x equals sine x. All right, we could also write that as d dx, so take the derivative of sine x, and we get cosine x. All right, so hopefully that gives a little bit more of a justification for where that comes from, which I know it can be a little bit of a stretch when we're just looking at formulas. Here they are without any basis. So I wanted to be sure that you saw that. Now, if we move on, there are 3 more, and I will do side videos that you can watch if you'd like to, that'll give a basis for cosine x and e to the x, and it'll be the one that I talk through with the other half of the class. But if we get to ln of x, we used to always present that much later in the year, and we chose to present it early just to avoid really cutting out a lot of the real life applications that we could do when we get towards our 4th and 5th unit, where it's all applied derivatives. Any real life growth situation really is based on an e to the x or an ln of x. So if we don't have those derivatives, we're very, very limited. So if I go in on these, I'm right now just going to tell you what they are. So derivative of cosine x is negative sine x. Derivative of e to the x is e to the x. And derivative of ln of x is 1 over x. All right, now with these, that basically will let us do any of those problems that we saw throughout the homework. A lot of them really look like find the derivative of things like this: sine x plus e to the x minus ln of x. And we just had to be comfortable taking each piece and saying, okay, derivative of sine x is cosine x. Derivative of e to the x is just e to the x. And the derivative of ln of x is 1 over x. All right, and that's how most of those questions play out. All right, so that's the quick little recap of the material from the last homework set that you had. Hopefully that gives you a little bit more basis. Again, like I said, you'll have a short video available with some justification for those two. And we will have to circle back around at the end of the year on ln of x to give some justification for that. All right, so I hope this video helped give some basis for the derivative of sine x. I'll be back with more in a little bit.